Hello everyone. Today we will discuss few topics and then we will discuss questions based on these topics. First topic, Gaussian quadrature. It is a numerical integration method used to approximate the definite integral of a function f of x over a finite interval a to b. It involves finding the optimal set of weight and nodes that minimize the error of approximation. The method is based on idea of using weighted sum of function valued at specific point within the integration interval. The Gaussian quadrature formula can be expressed as this, where Wi and Xi are the weight and nodes respectively that are chosen to minimize the error of approximation. The weight and nodes are specific to a particular quadrature rule being used and are calculated using orthogonal polynomial. There are two types of Gaussian quadrature rule, open and closed. Open quadrature rule do not include the endpoint of integration interval, while closed rule include them. The choice of the type of rule depends on the nature of function being integrated. The most commonly used Gaussian quadrature rule are Legendre, Hermite, Legendre, and Chebyshev quadrature rule. The Legendre quadrature rule is used for integrating function defined over the interval -1 to 1, while the Hermite, Legendre, and Chebyshev quadrature rule are used for integrating function defined over other intervals. The accuracy of quadrature method depends on number of nodes and weight used. With higher accuracy require more node and weight. However, increasing the number of nodes and weight also increase the computational complexity of method. Overall, Gaussian quadrature is a powerful method for numerical integration, offering high accuracy and efficiency compared to other numeric integration methods. Next topic is Gaussian Legendre. This formula is a type of Gaussian quadrature method used to approximate the definite integral of function f of x over a finite interval a to b. It is based on Legendre polynomial and involves finding the optimal set of weight and node that minimize the error of approximation. The Gaussian Legendre formula can be expressed as this where Wi and Xi are weights and nodes respectively that are specific to Legendre polynomial of degree n and are chosen to minimize the error of approximation. The weight and nodes can be calculated using the root of Legendre polynomial of degree n. The Legendre polynomial of degree n is defined by following recurrence relation. P0 of x is equals to 1, P1 of x is equals to x, Pn plus 1 of x equals to 2n plus 1 into x, Pnx minus nPn minus x divided by n plus 1. The node xi are the root of Legendre polynomial of degree n and weight wi are given by wi is equals to 2 whole divided by 1 minus xi whole square into Pn minus 1 xi in की power 2. The Gaussian Legendre formula is a closed quadrature rule, meaning that it includes the endpoint of integration interval. It is most commonly used Gaussian quadrature rule, and it is particularly effective for integrating smooth function over the interval -1 to 1. The accuracy of Gaussian Legendre formula depends on degree of the Legendre polynomial used and number of nodes and weight. Higher accuracy can be achieved by increasing the degree of polynomial using more nodes and weight, but this also increases the computational complexity of the method. Overall, the Gaussian Legendre formula is a powerful method for numerical integration, offering high accuracy and efficiency compared to other numeric integration methods. Next topic is Newton-Cotes formula. It is a family of numeric integration method used to approximate the definite integral of a function f of x over a finite interval a to b. These methods approximate the area under the curve of the function f of x by approximating it with a series of equally spaced points and using polynomial interpolation to approximate the function between these points. The most commonly used Newton code formula are the trapezoidal rule, Simpson's one-third rule, and Simpson's 3/8 rule. These formulas are named after their inventor, who were mathematicians of 17th and 18th century. The trapezoidal rule approximates the function f of x by straight line between the endpoint a and b. Simpson's one-third rule approximates the function f of x by a quadratic polynomial between three equally spaced points. Simpson's 3/8 rule approximates the function f of x by a cubic polynomial between four equally spaced points. The accuracy of Newton codes formula depends on number of equally spaced points used to approximate the function f of x. Generally, as the number of points increases, the accuracy of approximation improves. However, the computational cost also increases with the number of points. One limitation of Newton code formula is that they assume that the function f of x is smooth and well behaved over the integration interval. If the function has a sharp change in slope or discontinuity, the accuracy of approximation may be reduced. Despite their limitation, Newton codes formula are widely used for numeric integration, especially when the function is relatively smooth and the number of points used for approximation is small. They provide a simple and effective way to compute numerical approximation for integrals and are essential tool in many scientific and engineering applications. Trapezoidal rule, as we have seen above, it is a numerical method used to approximate the definite integral of a function f of x over a finite interval a to b. It approximates the area under the curve of a function f of x using trapezoid, hence name trapezoidal rule. The formula for trapezoidal rule can be expressed by this, where f of a and f of b are the values of function at the endpoint a and b respectively. The trapezoidal rule approximates the area under the curve of a function f of x by approximating it with the series of trapezoids that connect the function value at the endpoint a and b. The area of each trapezoid is equal to the average of the two function values at the endpoint multiplied by the length of the base, which is the difference between b and a. The total area is then approximated at the sum of area of all trapezoids. The accuracy of trapezoidal rule depends on number of trapezoids used to approximate the area under the curve. As the number of trapezoids increases, the accuracy of approximation improves. However, computational cost also increases with number of trapezoids. One limitation of trapezoidal rule is that it assumes that function is linear between the endpoint A and B, which may not be the case for all functions. This can lead to significant error in approximation, especially for functions with large changes in slope over the integration interval. Despite its limitation, the trapezoidal rule is a simple and widely used method for numerical integration, especially for functions with relatively few change in the slope over the integrational interval. Next, we have Simpson's one-third rule. It is a numerical method used to approximate defined integral of a function f of x over a finite interval a to b. It is a type of numerical integration method that uses a quadratic approximation to function over each interval of length h, which is equals to b minus a by 2. The formula for Simpson's one-third rule can be expressed by this, where f of a and f of f of a and f of b are value of function at the endpoint of interval, and f of a plus b by 2 is the value of the function at midpoint of the interval. The Simpson's one-third rule is based on the idea of approximating the area under the curve of a function f of x using a parabolic approximation, which is based on three equally spaced points. It is more accurate method of numerical integration compared to trapezoidal rule, which uses a linear approximation of function. The accuracy of Simpson's one-third rule depends on smoothness of a function being integrated and number of subinterval used. Generally, increasing the number of subinterval leads to more accurate approximation of the integral. One limitation of Simpson's one-third rule is that it requires an even number of subintervals. In case where the number of subinterval is off, Simpson's one-third rule cannot be combined. Can be combined when trapezoidal rule to obtain a more accurate approximation of integral. This method is called Simpson's 3 by 8 rule. Overall, Simpson's one-third rule is simple and efficient method for numeric integration, providing accurate result for smooth function with relative few subintervals. Next, we have Simpson's 3 by 8 rule. It is a numeric method used to approximate the definite integral of a function f of x over finite interval a to b. It is a modification of Simpson's one-third rule and is used when the number of subinterval is odd. The formula for Simpson's 3 by 8 rule can be expressed by this, where f of a, f of b, and f of a plus h and f of a plus 2h are the values of the function at the endpoint and the midpoint of two subinterval of length h, which is equals to b by a minus b minus a divided by 2. Like Simpson's one-third rule, Simpson's 3 by 8 rule is based on approximating the area under the curve of a function f of x using quadratic approximation, but instead of using quadratic approximation over each interval of length h equals to b minus a by 2, Simpson's 3 by 8 rule uses a cubic approximation over each interval of length h equals to b minus a by 3. The accuracy of Simpson's 3 by 8 rule is generally higher than Simpson's one-third rule for same number of function evaluation, but it requires more evaluation of a function. In practice, Simpson's 3 by 8 rule is often used as a refinement to Simpson's one-third rule when the number of subinterval is not even. One limitation of Simpson's 3 by 8 rule is that it requires the function to be smooth over the integration interval. If the function has discontinuity or sharp change in slope, the accuracy of method may be reduced. Overall, Simpson's 3 by 8 rule is a simple and effective method for numeric integration when the number of subintervals are not even, providing accurate results for smooth function with relatively few subintervals. Now we will discuss a question based on the topic we have seen above.